Let me thank the organizers for the invitation to speak here. It's my first time in Russia and I'm quite happy to be here. So I'll talk about injectivity of spherical means on H-type groups. So I will spend a couple of minutes on the Euclidean spaces and then go to the Heisenberg group, describe a result by Thangavelu, and then we'll see how it takes shape in H-type groups. Okay, so let's start with spherical means on Rm. So the question is, can you determine a function by its averages? Okay, so since we are talking about spherical means, we'll be talking about averages over spheres. Okay, so you fix a radius r and look at all spheres of radius r in Rm and take the function's average over those spheres and see if you can get back the function. Of course, if you want to get back the function, the operator should be injective, right. So that is the question we will be looking at. So spherical means on Rm, the averages over the spheres can be written as a convolution. So you look at the normalized surface measure on the sphere of radius r and look at the convolution with f, that's precisely the average of f, right. These are the spherical means. Okay. So keep the notation, nu r is the normalized surface measure on the sphere of radius r centered at 0, and you are looking at average of functions. And so the question we are interested in is if f convolved with nu r is 0 as identically, then can you say f is 0, right. So that would be the injectivity question we are interested in. Okay. Well, so let's look at some counter examples to start with. So look at the exponential function e to the I x naught dot y. So we are on Rm, and when you convolve the exponential with a measure, you get the Fourier transform of the measure times the exponential. So you will get this value nu r hat at x naught equal to 0 if the exponential is such that the x naught is a 0 of the Fourier transform of the measure, right. And the Fourier transform of the measure is explicitly calculated to be a Bessel function. So you can do a little bit more because the function the measure nu r is rotation invariant. So you can radialize this exponential and you will get a Bessel function. So that's what I denote by phi sub lambda. So for lambda positive, look at phi sub lambda. So you look at the Bessel function j m by 2 minus 1 lambda mod x by lambda mod x to the m by 2 minus 1, the usual Bessel function on Rm. And well, so because of whatever is written in the first line, this we have this product formula that phi lambda convolved with nu r is phi lambda times phi lambda r times phi lambda x. So phi lambda r meaning it's a radial function, so it makes sense to evaluate it at r, right. So that is the eigenvalue. So phi lambda can be thought of as an eigenfunction for this operator with the eigenvalue phi lambda r. So if you choose a 0 of a Bessel function as your radius, then of course the convolution will identically be 0. And you see that from the asymptotics of the Bessel function, you know that it will be in LP only if p is greater than 2m by m minus 1. Okay. So if you look at this injectivity question as an injectivity question on LP, the injectivity fails for p greater than 2m by m minus 1. Okay. So that is the range. So question is, what happens when p is less than 2m by m minus 1. Okay. So let's look at a general result due to Salzman. So this is from 1980. If I take two averages instead of single average, okay, so you have nu r and nu s, and then suppose the convolution is identically 0. So here the function f can be any continuous function, it does not have to be in LP, there is no decay. Yeah.
How do you denote the dimension of the space?
M. Yeah. Okay. Yeah. So f convolved with nu r and f convolved with nu s is identically 0. Then f is 0 provided the ratio of the radii r by s is not a ratio of the zeros of the Bessel functions j m by 2 minus 1. So the m is the dimension of the underlying space. But that's a two radius theorem, right? You need two radii for for injectivity to happen, R and S. So it was proved by Tangvelu in 94 that you have a one radius theorem. So remember that Bessel functions belong to LP for P greater than 2m by m minus 1, right. So for the range between 1 and 2m by m minus 1, you have injectivity. It's enough to look at one radius. Okay, so F convolved with mu r is 0 implies F is 0 if F belongs to LP for P less than or equal to 2m by m minus 1. So injectivity is true there. So now let's go to Heisenberg group. So Heisenberg group is the simplest of the nilpotent groups. It's a two-step nilpotent group. It can be identified with Cn cross the real line, where the real line is the center of the group. With the group law, Zt times Ws. So the Z and the W comes from Cn, T and S comes from the real line, and in the first coordinate it is simply the addition Z plus W, and you have T plus S plus a factor which makes it into a non-commutative group. Okay, so half imaginary part of Z dot W. So it's a two-step nilpotent Lie group, and we define spherical mean. So you look at the sphere in the Cn part, okay, and let's say mu r is the normalized surface measure on the sphere in the Cn part of radius r. So think of it as a measure sitting inside the Heisenberg group. So it has no mass on the center, no mass on the real line part, and then you look at the average of F over that, right. But now you are convolving in the Heisenberg sense, right. Heisenberg group, you look at the convolution on the group. So you have F convolved with mu r Zt equal to integral over mod W equal to r. So that is where your measure is supported, and whatever is coming inside is precisely the convolution definition, right. But that minus half imaginary part of C dot W bar will come because of the group law, right. So this is the spherical means. Well, there are various reasons or various justifications to say these are the spherical means on the Heisenberg group. Okay, we'll probably not get into that. Now the question is, whatever we did for the Euclidean case, we want to know if this operator is injective or not, right. If the convolution is identically 0, is it okay. So injectivity question. So F convolved with mu r is identically 0. Can you say F is 0? So it was proved by Tangvelu in the same paper. So I showed you the result for Euclidean spaces. It's the same paper. The injectivity holds true for P between 1 and infinity, including 1 but not including infinity. And a two radius theorem is also true. So remember Salzmann's two radius theorem, R and S, where R by S is not a ratio of the. So that is also true, and this was done by Agronowski, Berenstein, Derchin Chang, and Vasquez. This is more like a Wiener-Tauberian theorem for certain class of functions on the Heisenberg group. Okay, so yeah. Well, so why is the I mean, how does one determine the injectivity range? Of course, you can look at natural counterexamples and see which LP they belong to. That is one reason. The natural counterexamples seems to be radial eigenfunctions of the Laplacian. Okay, so in the case of the Euclidean spaces, it was the Bessel function. These are radial eigenfunctions of the Laplacian. In the case of the Heisenberg group, you have this slightly more complicated function. Ek lambda. Ek lambda is e to the I lambda t. So in the t variable, that is the central variable, it is simply an exponential e to the I lambda t times phi k lambda. What is phi k lambda? It is given by Laguerre polynomials Lkn minus 1 times an exponential Gaussian, right. So that is how the function looks like. So the function is quite nice in the z variable, right. It is a Schwarz-Class function, so polynomial times a Gaussian. But in the t variable, it is simply an exponential e to the I lambda t. It has no decay, right. It belongs only to L infinity, right. Because in the t variable, it has just modulus 1. So it belongs only to L infinity. So that is why you have the injectivity range for the Heisenberg group to be 1 to infinity. Okay, the natural counterexamples fall into only L infinity. Other ranges it is not. Now, if you recall, for the Euclidean space, we had a product formula for the Bessel function. Phi lambda convolved with the normalized surface measure was, so it was an eigen function, right? It was phi lambda r times the same function. So we have a similar product formula. So all these are part of the Gelfand pair theory. So I'll not get into that. The Ek lambdas also satisfy a certain convolution equation, that if you convolve with these measures, normalized surface measures, you will get this phi k lambda r. So again, phi k lambda r makes sense because it is a function of mod z square. So you will have Lkn minus 1 half mod lambda r square times the Gaussian. So that is the eigenvalue in this case, and this Ek lambdas belong to Lp if and only if p is infinity. So that is why you have the injectivity range for from p equal to 1 all the way to infinity, but not including infinity. Okay, so all right. So now we can go to H type group. So what I want to describe is a result of mine with two others. On H type groups. So what are H type groups? H type groups are Heisenberg type groups. So slight generalization of Heisenberg group. Think of H type groups as Heisenberg group with a larger center. So in the usual Heisenberg, you have the center to be just the real line, which is one dimensional. For H type groups, you can have any dimensional center, any bigger center, but the harmonic analysis and representation theory of these groups are more or less similar. Okay. All right, so we start with a two-step nilpotent Lie algebra. One of the advantages with nilpotent Lie groups is Lie algebra and Lie group can be identified, and you can put the group law on the Lie algebra itself. Okay, so you can write this as V direct sum Z, where Z is the center of G, and it's an orthogonal direct sum. So you can put an inner product so that this happens, and nilpotent Lie group associated to this nilpotent Lie algebra can be identified with the Lie algebra itself. So you put a group law on the Lie algebra. So let us see how the group law is. Group law is very simple because it is two-step. I have V1 C1 V2 C2. So V1 and V2 comes from capital V, Z1 Z2 comes from Z, which is the center of the Lie algebra. And the group law is simple. In the V coordinate, it is simply addition. So remember the Heisenberg case, it was Z plus W, just addition in the first Cn part. Only in the central part there is a difference which makes it into non-commutative. There it was Z1 plus C2 plus half bracket of V1 V2. Bracket is the Lie bracket. So remember the half imaginary part of Z dot W bar in the Heisenberg case. It's the same. In the Heisenberg case, you will get exactly. Now these groups were introduced by Kaplan in the 80s. The group is called H type if you have a certain condition. Okay, so I will not spend too much time on it. I will just define what it is. For each central element Z, you can define a map from V to V. So remember, V is the complement of the center. Okay, defined by that. GZV inner product with V prime is something. Okay, that actually defines a map from V to V. One has to check that. The group is called H type. So this H type meaning Heisenberg type. If JC square is minus mod Z square times identity. Okay, so on V you have a map which has satisfies certain conditions. Okay, that is what you mean by an H type group. So what is the condition? JC square is something times minus something times identity, which says that the dimension of V has to be negative, right? If I take a central element Z which has modulus 1, then I have a map whose square is minus 1. So that means it has to be even dimension. So think of V as some Cn, right? Because it's even dimension, I think of it as Cn. And then the center part is Rm. It can be a bigger dimension. Okay, if the Rm is simply the real line, then it is the Heisenberg group which we saw earlier. So it can be identified. So for all practical purposes, think of it as Cn cross Rm, okay, with a certain group law. Now you ask the same question, what are spherical means? Can you prove injectivity result for these spherical means? Okay, so let us define spherical means. So this is one way of defining. There are three means you can define. I will talk about only one of them. So you look at the spheres in the Cn part. So remember you have Cn cross Rm, right. So you look at spheres in the Cn part and then look at the convolution. Okay. So if mu r is the normalized surface measure, you look at f convolved with mu r. Now you are on the group G. So convolution is on the group G, and just like the Heisenberg case, you can write down what it is. Okay. So you will have z minus w t minus that half bracket zw comes because of the group law, right, which makes it into non-commutative. So the main theorem is the spherical means defined above is injective in the range 1 less than or equal to p less than or equal to 2m by m minus 1. So what was m? Remember the previous slide, the G is identified with Cn cross Rm. Rm is the center. So m is the dimension of the center, and you have the range 2m by m minus 1, 1 up to 2m by m minus 1, where m is the dimension of the center. Okay, so in the Heisenberg case, remember it went up to infinity because m was 1. So that is, if f convolved with mu r is identically 0, then f is 0 provided f belongs to a certain LP class where p is between 1 and 2m by m minus 1, including the endpoints. Okay, so I'll try to give a sketch of the proof. I am not going to get into too much of details. Is it possible to write on the? Okay, we'll continue. So what are the tools we need? We need a spectral decomposition of the sublaplacian on G. So remember, on the Heisenberg group there was a sublaplacian, and the the spectral decomposition with respect to that sublaplacian is needed. That is one. And this decomposition, so this converges in L2, that is the usual spectral theory, but we need convergence in LP. So we will prove the Abel summability in the LP sense. Then we need product formula for these eigenfunctions of the sublaplacian appearing in the spectral decomposition. So remember those two formulas we had, phi lambda convolved with a measure is because it was an eigenfunction. Similarly in the Heisenberg case. So here too we need the radial eigenfunctions that appear in the spectral decomposition to satisfy this eigenfunction equation. And we need an extra thing, which is the decay of functions whose Euclidean Fourier transform is supported on spheres. I will come to that when I. So let's see the sketch of the proof. So this is quite simple. So I'll just to make sure that the EC one can follow the these steps. We'll do this for the circle, which is the simplest case. Okay. So think of a function g in let us say LP of the circle. So this has a spectral decomposition, right? So what is the spectral decomposition? So this is the Fourier series g hat k e to the I k theta, right? So that is the first thing there. So sorry. So that is the first thing. The EKA. So remember, for the Heisenberg group it was EK lambda. Here it is EKA. You have e to the I a dot t, right? Because you are in Rm, not in the real line. So you take the inner product times whatever is remaining is something you have already seen, the Laguerre polynomial times the Gaussian. So that is why it's very similar to the Heisenberg case. You have a spectral decomposition. So the spectral decomposition is not as simple as what is written for the Fourier series. It has, so for each k you have an integral over Rm. Okay, so think of so for the Heisenberg case, Rm will be the real line. So you have these lines. Okay, so this is called the Heisenberg fan. So the spectrum of the sublaplacian is something like this. Okay, so for in this case each line is like Rm. Okay, so that is a spectrum. So think of disjoint union of various Rms. Okay, now the spectral projection, so you project it to the kth piece, you will get that integral of Rm f convolved with those radial eigenfunctions. So that is one result we have to prove, that it is bounded on LP. Okay, so here the spectral projection is trivial, right? It is just g hat k times e to the I k theta. That's a bounded operator on LP. Okay, that is easy. But here one has to prove. So how does one prove that? So if you look at it, you will see that it's a convolution operator. F convolved with something. Think of the integral inside, and those ek etc. are given by Laguerre polynomials times the exponential. Okay, so you can prove that it has a certain homogeneity, and it has the mean value property, and one, so it's a standard Calderon segment kernel on the nilpotent group, and then the Calderon segment theory applies. Okay, so first it's different from what is there on Rn, but this is the result which is well known on Rn. If you have a mean value 0 kernel which satisfies certain homogeneity condition, it's a bounded operator on P. That's precisely what is done here, but one needs the results for the nilpotent Lie groups. Okay, that was a result by Stein and Knapp. Well, they proved the L2 boundedness, and Korani and Wagi, I don't know how it's pronounced, those two proved that if you have L2 boundedness, you have LP boundedness. That's, so this mirrors the whatever is there on R. Okay, that's precisely what it is. And then you need Abel summability. So Abel summability is here, you will put an R to the K and take R going to 1, so that is a Poisson integral and so on. Here it's slightly more different, but the method is the same, because you have a summation, you put the summation inside, it becomes F convolved with some kernel, but the summation you can compute up to some point, because you have those LKs, those are the Laguerre polynomials, and you have a generating function for that. So you can do that, and you will get a certain complicated expression. You can't compute it explicitly, you know it's Fourier transform, but you will not be able to compute the kernel explicitly, but you can prove that it has the homogeneity property and cancellation conditions again, so the Calderon segment theory applies. Okay, so you can do that. Okay, so now last slide, we can prove the injectivity once we prove all this. So how does the proof go? First thing is, you prove that the EKA, the radial eigenfunctions appearing, has the product formula. Okay, so here if I have a measure and I convolve with e to the I k theta, I'll have the Fourier transform times e to the I k theta, right? That's precisely what the property there is. Now if I have the convolution to be 0, because of the Abel summability, I have this. Okay, so what does it say here? If I look at G convolved with mu, and suppose this is identically 0, what I have is G hat k mu hat k e to the I k theta, this is 0, right? But it's an LP function, so it has the Abel summability property, R going to 1, so this is 0, right? That is what is written there. F convolved with some UR is 0 will imply the in between the alpha k mod A comes from the eigenvalue, right? When I convolve, I get mu hat k here, there I get that complicated expression. The explicit expression is explicitly known, but what is important from our point of view is it depends on mod A. Remember, A comes from the center Rm, so mod A gives spheres in Rm. Now you apply projection, the kth projection. So here if you apply the kth projection, so this is a sequence of functions going to 0 in LP. So if I apply the kth projection, since projection is bounded on LP, I will get the kth piece, right? So apply projection, you will get limit R going to 1, R to the k, G hat k. Of course in this case this is all trivial, okay, I am only trying to explain what is happening there. The limit R going to 1, R to the k has nothing to do with, so you will get this is 0, right? That's precisely what is written there. This projection, the kth piece will be 0. Now the kth piece, if you look at the kth piece explicitly, this is now Euclidean analysis. The EKA, remember, is the exponential times the Laguerre function. The exponential tells me that the Fourier transform of some function is supported on the 0 z of that alpha k mod A, but alpha k mod A is the 0 z will be spheres, because it's a function of mod A. So I have a function on Rn, so think of this as a Euclidean problem now. I have a function on Rm in LP whose Fourier transform is supported on spheres. Then the maximum it can be in 2m by m minus 1. It can have at most decay like the Bessel function, you can't have more. So if your function comes from LP for p less than or equal to 2m by n minus 1, then it has to be 0. So that is how injectivity is put. Okay. So I think that I'll stop here. Thank you.
Thank you. Thank you very much, Professor Narayanan, for very nice presentation.